All right, here is our first video for our new online venue. I don't know if you've watched any of my videos before, but I think it's going to be really important for you to try to watch these videos as we make our way through the material in the next couple weeks. We are going to be having sort of face-to-face meetings with the Zoom app, where we can be a little bit more interactive, but I'm hoping that you will find these helpful as we learn new material. So in our new chapter 11, we're basically looking at magnetism. So it's in general, the big part of this semester is E and M. We've done a lot of work with the E, the electric stuff, and now we're going to get into the M, the magnetism. So we'll think about magnets and how they interact, which is probably stuff that we know. We're going to mainly be focusing on forces that exist when you have magnetic fields. So two different examples will be when you have a charge that's moving in a magnetic field, it feels a force. And also if you have current flowing and it's exposed to a magnetic field, again, it'll feel a force. We will try to differentiate between magnetic field lines and electric field lines to just help us compartmentalize them and find similarities and differences, and that sometimes helps us put everything in order in our head. And then at the end of this chapter, we're going to put some of that information together and look at how if you have a whole loop of current, a closed loop, and you place it in a magnetic field, because of the forces that are exerted on the different parts of the loop, you can actually have it rotate, so you have a torque. So I wanted to sort of show this picture from your book to begin with because it has a couple different things that should be familiar to you. As we get into the magnetic field, we want to think about how, like what we know and what makes us comfortable. So here is the Earth, and you probably know that the Earth has a magnetic field. That's how a compass works. If you didn't know, in a compass, like a handheld real compass that you might have, if you're a Boy Scout or, maybe a Girl Scout too, that needle in the compass is actually a magnet, and it aligns itself with the magnetic field of the Earth. And that's what they're trying to sort of illustrate in, right here when we see these little things in this picture. Those are trying to show like what a compass might look like at that location. And you can see that it's lined up with the blue lines, and those are the magnetic field lines of the Earth, because the Earth does have a magnetic field. The other thing that they're showing in this picture is that there's this bar magnet in the middle of the Earth, and the reason that they have that pictured is because it turns out that the magnetic field of the Earth looks a lot like what it would look like if there was a giant bar magnet in the middle of the Earth. And so it's a good approximation. The magnetic field lines that a giant bar magnet would create are pretty similar to the magnetic field lines that we have for the Earth. One of the things that is interesting when you think about this idea is, well, first of all, as a side note, in a magnet, instead of having positive and negative charges, we have poles, the North Pole and the South Pole. Turns out that every magnet has both, a North Pole and a South Pole. We'll learn later on in the next chapter that a basic tenet of electromagnetism is that you can't separate these. I can't cut that bar magnet in half and have just a North Pole and just a South Pole. But anyway, one of the interesting things when you look at this picture really closely is notice that when we're looking at the geographic North Pole, which is, up here, it's actually really close to the magnetic South Pole. Notice that there's two lines. There's this black line is like the rotation axis of the Earth, and then the red line is like the magnetic axis. and they're not exactly aligned. The way that we usually think about it is they are, but it's not a bad approximation. If you study other planets, you'll find that this is often the case, that the rotation axis of the planet is slightly shifted from the magnetic axis. But in any case, we know that we use a compass to find where the geographic north is. And the reason that it works is because the north pole of the needle of the compass actually is attracted to the south pole of the magnetic field of the Earth. And so it turns out that this is why at the geographic north pole we would find a magnetic south pole. All right, another, like some pieces of information about the magnetic field is, how do we measure it? We measure it in what we call Tesla, because of Nikola Tesla, a scientist from a ways back. We use the letter B to represent the magnetic field. And if you use another unit of magnetic field that you might see used is the Gauss, which is a smaller unit. I think it comes in handy because the magnetic field of the Earth is kind of weak, so it makes more sense to order it to express it in Gauss rather than Tesla. And so, as they say here, the magnetic field of the Earth is about 10 to the minus 4 Tesla, which is 1 Gauss. 1 Gauss. Okay, so now we're going to talk just a little bit about how the electric field and magnetic field are different. And I'm going to write two expressions for the force. Now, for the magnetic field, you might have, hopefully you've read about it in your chapter, but we haven't really introduced it yet today, but we're going to still use it to find some similarities and differences. So this is the expression for the force on a charge when it's in an electric field, and this is the expression for the force on a charge when it's in a magnetic field. So what do we see here? Let's just think about things that we know. We know that if Q is positive, the force is in the same direction as the electric field. If Q is negative, then the force is opposite the electric field. We learned that before. Here, now it probably is going to be necessary for you to review cross products or vector products, because we use a vector product to express the force of a charge due to a magnetic field. We're going to talk about it a little as we go, but again, it might be something for you to review. You might have seen it last semester when you talked about torque. That was a good example of where you used the cross product before. Here, if you remember the properties of a cross product, the force is actually perpendicular to both the velocity of the particle and the magnetic field. So now that's a little bit different. The force direction does depend on the sign of Q. That's a way that it's similar to the electric field. But something that's interesting here is if the charge is not moving in the magnetic field, then the force is 0. Where here, if the charge isn't moving, it still feels a force. So that's something that's a big difference from electric fields and magnetic fields. Another thing, if you remember, if the velocity is parallel to the magnetic field, there's no force. And so that's something that's kind of interesting. Later on, we'll learn that the force that the charge feels when the charge is in a magnetic field, that force can't accelerate the charge. Well, it can't change its speed. Sorry. It can't make it go faster, where this force can change the speed. Those are just some of the differences and similarities of the force that a charge feels in the electric field and the magnetic field. Again, some of these things we're going to kind of get into more detail as we move on. Okay, so here are some pictures showing magnetic field lines in different scenarios. There's the magnetic field lines just for a bar magnet, which we kind of saw when we saw the picture of the Earth. One of the things that isn't really shown in this picture is that these field lines are actually continuous in that they always form closed loops. They don't begin and end, so we shouldn't imagine that this line begins at the North Pole and ends at the South Pole, like we saw with electric field lines beginning and ending on charged particles, on different charges. Instead, for a magnetic field line, they always go in a complete loop. But as the book says, or as we see here in the caption, they just didn't show all the closed loops because it would make the picture too busy. Here we have two unlike poles close to each other, and we see the magnetic field lines going between them. And this is more representative of the fact that they're attracting each other, where you can see the repulsion in the third picture when you have two like poles close to each other. So for poles, magnetic poles, the North Pole and the South Pole are called magnetic poles. The same rules apply that apply for charges, and that is unlike poles attract, and then like poles repel. All right. So I'm sorry, my caption here got a little messed up. So here we're starting to think about how we find the force on a charge moving in a magnetic field. And just to find out how big it is, we can use this expression where the force is equal to the magnitude of the charge. Well, if it's negative, you can use a negative sign. The speed, the magnetic field, and then the angle between the two. And so in this picture, this would be the theta. And so from that, you can come to some conclusions about when the force is going to be the largest and when it's going to be the smallest, thinking about that angle theta. If we want to express this expression in terms of the vector product, so in the previous slide, we were just talking about how big the force was. We weren't really talking about the direction of it. But to understand the direction of the magnetic field, of the force due to the magnetic field, we have to use the cross product. It's a cross product of the velocity vector and the magnetic field. So for instance, in this picture, they're trying to show in the shaded plane is where the magnetic field lies. And then the velocity vector here is in that plane as well, but it's perpendicular to the magnetic field. And then because the force is the cross product of the velocity and the magnetic field, the force is perpendicular to both of them. And we would use the right-hand rule to figure out that direction. Using this expression for the magnitude of the force on a moving charge in a magnetic field, we find that if the angle between the magnetic field, again, remember this is the angle between the velocity and the magnetic field. Now, if that angle between the two is 0, which would be this case, the force is 0 because of the fact that the sine of 0 is 0. Now, if the angle between the two is 180, which means the V is opposite the magnetic field, the force is also 0, and that's this case right here. So you see that what happens if the velocity vector is in the same direction or the opposite direction of the magnetic field vector, the charge doesn't even really feel any force because of the magnetic field. It in a sense, doesn't even notice it and won't be affected at all. The opposite case of that is what we saw in the previous slide, when the angle between those two, velocity and magnetic field, is 90 degrees. That's when you get the largest force. And this is what the picture is here. Here again, we see that because in this case, that's 90 degrees. And so the sine of 90 is 1, and so you get the maximum force for the charge moving in the magnetic field. So you keep seeing these directions of this force, and you might not know how can you figure out the direction of that force. But hopefully last semester you did learn the right-hand rule for finding the direction of a vector that's the result of the cross product of two vectors. So in this picture, they are showing sort of how you would find that direction of that force. When you have a cross product, and that's what we have right here, you first take your hand and you lay it along the direction of the first vector, so that would be the velocity vector. And then you curl your fingers towards the magnetic field, and you can kind of see in this picture how those fingers are curled, and they also are showing this arrow, and that's the way you're curling your fingers. And you know, your fingers only go one way because you can't bend your fingers backwards. And if you position your hand so that you can curl your fingers in the direction of the magnetic field, then the way that your thumb points is the direction of the cross product. And so for this case, it's the direction of the force. That would be as long as Q is positive. If Q is negative, then you have to flip it, and then that's the direction of the force. So because of the way that right-hand rule works, that's how we find that the force is perpendicular to the velocity in the magnetic field. Now this one you could sort of try. The best way to do this is to imagine the shaded plane is like a piece of paper that's coming out at you and that's perpendicular to the screen, and the velocity and the magnetic field are on that piece of paper. So I kind of have my fingers pointing out, and then I curl them towards the screen because that's towards the magnetic field, and my thumb points up. And for a positive charge, that's the direction of the force, because for a positive charge, the force is in the same direction as V cross B. If you put a negative charge in front of there, then V cross B gives you the direction, and then you put the minus sign in front of it, and that flips it. So here are some pictures where they're doing the right-hand rule. Again, think about how we would lay our hands along the velocity vector, curl our fingers towards the magnetic field, and the way that our thumb is pointing is going to be in the direction of the force. In the second picture, notice how the velocity is kind of back towards the screen, and so you actually would have to hold your hand so your thumb's pointing down, because then when you want to curl your fingers towards the magnetic field, your thumb points down, and that's direction of the force. I know that it's hard to do this right now, and so this is something that maybe we can go over in a little bit more detail when we have our Zoom meeting, and we can have have some video. In this picture, because the charge is negative, when we do V cross B, so in the top picture, our V cross B would actually give something that would point up, but then because it's a negative charge, the direction of our force is opposite of that, and that's why it's down. Similarly, for this picture, V cross B would point down, but because it's a negative charge, you put that negative sign in front of this, and that gives you the force up. It's something to remember. With the negative sign, you always have to flip and go opposite from what your right-hand rule told you. And in this picture is kind of nice because it's showing the opposite charges with same velocity and magnetic field, but then they're right next to each other, and you can kind of compare how with the positive charge the force is in one direction, it's in the same direction as V cross B, but for the negative charge, if you do V cross B, you would get up, but then you put the negative sign in there, and that's why the force is down. Okay, so one of the interesting things that we find is this particular motion of a charged particle in a uniform magnetic field. So this is an important notation. And so when we see a lot of X's, and this is how we're trying to show things that are three-dimensional on a two-dimensional piece of paper. So, you know, we can easily show something that moves up or something that moves to the right on this piece of paper, but what about something that goes into the page or out of the page? And the way that we do that is with X's, and then also with dots is out of the page. And so into the page means it's going into, out it would be coming right at you. I think a handy way to keep this straight is to think of an arrow. And if the arrow was going into the page, you would see the back of the arrow where the feathers are, and that's why you see the X. And if the arrow is coming at you, if it's coming out of the page, you'll see the point of the arrow, and that's what that is. Okay, hopefully that helps. All right, so when you have a charged particle moving in a uniform magnetic field, and so the fact that all these X's are equally spaced means that the magnetic field is uniform. It means that everywhere that we look, it has the same strength and the same direction. And if we did V cross B, if we laid our hand along that velocity vector and then curled our fingers into the page, we would have a force up. And so what would happen is that's going to deflect the velocity of the charged particle, and so now it's going to look like this. And then if we do that V cross B again, what's going to happen is it's going to continue to get deflected. So what happens is, think about this, the force is always going to be perpendicular to the velocity, and if we think about what's going to happen over time, the charge is going to get deflected and start moving in a circle. Remember what this is? This is a centripetal force because it's perpendicular to the velocity, and it's kind of makes the object go in a circle. So when a charged particle goes into a magnetic field and is moving perpendicular to that magnetic field, it will actually start going in a circle. And that's an important type of motion that we see in nature. Back to this picture, our particle is going in the counterclockwise direction, and it's a positive charge, and it was initially moving to the right with a magnetic field into the page. In this picture, if you kind of go back and forth, notice that let's see what happened if almost everything is the same. The charged particle initially is moving to the right, the magnetic field is into the page, but now the charge is negative, and so when we did V cross B, here we thought the V cross B was up, but that means the force is down because of the negative charge, and the charge starts moving in a circle, but it goes in the opposite direction. Here, this one goes clockwise. So there's things that we like to think about for that circle, like what kind of things do we know? And one of the ways that we can easily find some relationships is we think of the fact that the force acting on the charge is equal to the mass times acceleration. And because of the fact that the velocity and the magnetic field are perpendicular, the force that the charge feels is just QVB. And because it moves in a circle, we can write the acceleration as V squared over R, because that's centripetal acceleration. So one of the things that we like to know is, what is the radius of the circle? So we could rearrange these values, and we'd have mv squared over qvb, which actually we can get rid of one of the v's. And so it turns out that the radius of the circle depends on the mass of the charge, its speed, what the magnitude of its charge is, and the strength of the magnetic field. So that's something to remember. You're going to see a couple different relationships, and my recommendation is you remember this, and then you rearrange it to find what you want to know. If we wanted to know what the angular frequency of the particle is, you might remember, or the angular velocity is V over R. That's back from first semester. And we could think about how we could rearrange these expressions to find V over R. And we would find that it was equal to QB over M. That's okay. But actually, the reason that I found that value isn't so much that I'm not interested in the angular velocity, although you might be asked to calculate it, is remember that angular frequency is related to regular frequency through this relationship. And if we solve for F, it's QB over 2 pi m. And this has a special name. It's called the cyclotron frequency, because there are actually machines that they make to try to contain charged particles in a plasma. And they do that by making magnetic field lines, and the charged particles will go in circles around them. And one of the things they like to measure is, what is the cyclotron frequency? Like, how fast are they going in those circles? You can also find the period. How long does it take it to go through one complete revolution? That's what the period is. Remember, that's inversely related to the frequency, and so we can use the expression we just found and just invert it. So those are just some of the things that you might be asked to find at different points, but keep in mind that if you just start with this equation, you can get to the other ones that you might want to know. I didn't need as much space to work as I thought. One of the things that is interesting, if you think about it, in terms of the force that a charge feels in a magnetic field, is always perpendicular to the velocity, which means generally, because the velocity will be just the change in its position over time, that is also, the force is also perpendicular to the displacement, which means that this force doesn't do any work. Which means that the work done is equal to 0, which is the change in the kinetic energy. And so the kinetic energy of this particle as it goes in a circle is constant, and which means that the speed isn't changing. It's one of those interesting things that we don't think much about, but once we see it, it seems pretty clear. One last thing that I wanted to mention is that, we started off with that cyclotron motion, assuming that the velocity was perpendicular to the magnetic field, but it's not always. Maybe it's at an angle, and when it's at an angle, we can break down the velocity into its components, but think of the component that's perpendicular to the magnetic field and the component that's parallel to the magnetic field. This component, the part of the velocity that's parallel to the magnetic field, is unaffected because that force that acts on that part of the velocity, it doesn't feel any force. And then the part of the velocity that's perpendicular makes it go in a circle. So what happens is you get two things happening at the same time, is that in the direction perpendicular to the magnetic field, the particle is going in a circle, but in the portion of the velocity that's parallel to the magnetic field, just keeps on going in that direction without any change. And when you combine the circular motion with the parallel motion, you actually get what we would call a helix. And this is something that's really very profound about how charged particles move in magnetic fields, because they actually move, they circle around the magnetic field lines. And we see that in, say, the Earth's magnetic field, charged particles will circle around the Earth's magnetic field line. And that's part of the reason that we see the aurora, is as they come down to our atmosphere, they're following the magnetic field lines because they're spiraling around them. And when they hit the atmospheric gases, they excite those atoms, and those atoms give off light from that excitement, and that's how we get the aurora. So that's where we're going to finish off with this first part of chapter 11. I hope you made it all the way through the video, and if not, at least hopefully you took a breather and then finished it up. So I'll give another video on some of this chapter 11 material for you, and we'll work through this together.